In 4.7, we briefly discussed acids and bases for neutralization reactions. So 4.8 is just going to talk in more detail about what happens for those reactions. So general definitions were suggested by Johannes Bronsted and Thomas Lowry at the same time, and even though they're from different countries. So that's why we call it the Bronsted-Lowry model, where an acid is a proton donor and a base is a proton acceptor. Remember that a proton is a hydrogen ion. Okay, so for example, when gaseous hydrochloric acid dissolves in water, each HCl molecule donates a proton to water to make, and that's what makes it an acid, because it is donating that proton. Okay, now this compound that's formed right here is called hydronium ion. So again, hydronium ion has a formula of H3O with a +1 charge, and that just comes from having your H2O molecule and combining another hydrogen with a +1 charge to it. And so sometimes, and we'll get into acids and bases later this year, we might just write H+, but what really happens is the hydronium ion is formed. So it's depicted right here in this reaction, and this is the same reaction where we have the HCl, the Cl is the big green compound that forms with water. When you have reaction of an acid with a base, or an acid dissolving in water, we have some things that are formed. So HA is generically used to represent acid, and in this case water is acting like a base, because if you have an acid-base reaction, one of the reactants has to be an acid and one of the reactants has to be a base. So we have an acid, then the water is the base. Then we form the hydronium ion and what's called a conjugate base. So the conjugate base is everything that's left over from the acid molecule after one proton is lost. So if we have just HA, then that is why it turns into A-. Okay? The conjugate acid is the product that gained the proton. Okay? And then a conjugate acid-base pair consists of the two substances that are related to each other. So you would either have the acid with the conjugate base, or you would have the base with the conjugate acid. Either one would be a conjugate acid-base pair. Okay? So in this example, I kind of already alluded to it, the two pairs that we have are HA and A-, so the acid and the conjugate base, and then the base and the conjugate acid out of there. Okay? So you might have to identify what would be the conjugate acid-base pair in a reaction from a list, multiple choice question. So just know that they are related. You wouldn't ever have the acid with the conjugate acid or the base with the conjugate base. They're always opposites that go together. Water is very special. We say it's amphoretic because it can act as an acid or a base. Water is the most common amphoretic substance that we have, that we know about. And that's because if you have the autoionization of water, where you have two water molecules combining together, what happens is one of them will donate, the H+, and one will accept the H+. Now, do I know which one really in real life does that? No. But when we do that, we create our hydronium, and then what's left over from one of the waters would be the hydroxide ion. So it's amphoretic because it can, it's amphoretic because it could go either way, okay? And you would just have to label one as an acid and one as a base in that type of situation. So hopefully this helps identify a little bit more about acids and bases to help you identify. Remember that the ionic equation for a neutralization reaction is going to be the H+ OH- makes water. All right.